Okay, thanks for your help and sorry for the trouble. Welcome everyone to the third and final lecture on event generation, pattern shows, and simulations. So yesterday, we finished the discussion by introducing the semi-classical matrix element. And today I want to start by discussing, or by deriving, yesterday we finished by deriving the matrix element. Today I want to start by discussing some of its properties, which despite the simple form of the matrix element are not entirely trivial. So we will discuss the dipole radiation pattern. And this applies to general gauge theories, so it applies to QED and QCD in the same way. QCD is of course a bit more complicated because it's an abelian, but we'll get there. So what we are going to do first is we take what we derived yesterday, this matrix element PA.PB over PA.PC, PB.PC. And as a reminder, A and B were the two initial charges. And then the C, momentum C, is what we radiate, okay? And we discussed that you can choose a convenient frame where you put A and B on the forward and backward direction, or on the light cone, if you will. And then you can write this conveniently as a 1 over transverse momentum squared. And we will get back to this in a minute. But what I want to do now is I want to go back to the, let's say, way this was rewritten in the 1980s in order to expose its properties in the collinear limit. So in order to do so, we will write it as something that I will call the angular radiator function, divided by the energy of particle c squared. So I said yesterday that nothing depends on the magnitude of the momenta A and B because they appear upstairs and downstairs in the same way, right? So in this thing, I can pull out the energy of C, and then what I have left over is this WABC, which is 1 minus the angle between A and B over 1 minus the angle between A and C, 1 minus the angle between B and C. And what's inconvenient about this function here is that it entangles two different collinear limits. So there's a collinear limit when A and C become parallel, and there's a collinear limit when B and C become parallel. That's because it was derived from a dipole radiation picture, right? So they should both be reflected in that matrix element. But if you want to derive the D-Glab equation, the randomization of the fragmentation functions or pattern distribution functions that Ian already spoke about this morning, then this is not so helpful. Because as you integrate over phase space, you will not only encounter the collinear limit that you care about, the kind of the evolution in the direction where the proton is flying, but also in the other direction. So you want to get rid of that. And in order to do this, we expose the individual singularities through an additive matching. Let me call this the forward collinear limit. By saying we write this WABC as a sum over two terms, sorry, ABC, where I'm interested in the collinear limit between C and A, plus the one where I'm interested in the collinear limit with respect to B. Okay, so how do I do this? In the simplest possible way, I'm saying, okay, I take half of the original. This is 1 minus cos 1 minus cos theta 1 minus cos theta BC. And I add the structure of the collinear propagator in terms of the angles in the forward direction, and I subtract this in the backward direction. Okay, so now as theta BC becomes small, the angle between B and C becomes small, this guy will cancel this guy and the rest will not matter. So you can check out that it really has no singularity in the backward direction. So this is divergent only as theta AC goes to 0. And it has another very convenient property. It also has an inconvenient property. The inconvenient property is that because I've done this additive matching here, the entire function can become negative because this term in the wrong region of phase space can overcompensate everything else. However, this only happens, I draw a picture here. This is the direction of A, this is the direction of B, and then I radiate something, C. Okay, so now this is theta AB. This is theta AC. And then there is an azimuthal angle here, which I will call phi for simplicity, phi C. Okay, this emergence of the root of this function only happens when the polar angle here becomes larger than the polar angle here. Okay, and we will see in a minute how this turns into the angular ordering property of QCD. Okay, so more precisely what will happen is as I integrate or average over the azimuthal angle, I find that this is just the structure of a collinear propagator that I would like to have times either 1 if theta AC is less than theta AB or 0 otherwise. So that means as I average over this azimuthal angle of the radiated parton, with respect to the collinear direction that I'm interested in, which is defined by my parton A here, by my initial radiating charge, I will either have something that looks like a collinear structure if the emission angle is less than the opening angle of the emitting color dipole, or charge dipole, if you will, or I will have 0 if the emission angle is larger. And this is an effect that has also been measured experimentally already in the 1950s, and it's known as the Rudakov effect. So you can measure this already in QED, because this is a property of a theory, of a gauge theory. It doesn't matter that it's not abelian, it also occurs in QED, okay? And it has to do with the fact that if I emit a gauge field quantum here, it has to have sufficiently small transverse wavelength to actually peak inside this emitting dipole and resolve the individual charges. Questions on that? Okay. Okay, so let me go into a bit more detail on this, because usually this result is just quoted, and then you go from there directly to angular ordered parton showers, but I want to develop a little bit more intuition about what this actually means and what one might want to do and might not want to do in a simulation when we implement this or not implement this. So the radiation pattern normalized function in the plane where I have cos theta AC here, so the polar angle between the emitter and the emission versus cos theta AB, then the angular ordered region is up here. Okay? Cos theta AC has to be less than cos theta AB, basically. Oh, sorry, theta, not cos theta, whatever. So this is the angle. But it doesn't matter so much. So the angular ordered region is up here, and I get this 1, okay? However, the matrix element is by no means 0 in this region, because it's only 0 when I integrate over the azimuth. And if I plot the contour lines of the matrix element in this region, then it looks somewhat like this. And down here in this corner, it actually goes to 0. So this is kind of the positive part. And then I have here, as the next one, the negative part. Because this is already 1, I cannot subtract anything more. So I get a 0 in this upper region. And then I can again plot contour lines. And because I know that I get 0 in the not angular ordered region, it also has to go to 0 here. It has to be exactly the same but opposite, right? So on this diagonal, the matrix element is also 1 if I normalize it conveniently to this function here. And then it goes to 0, but it's completely negative, right? So this is the minus part of this integral, if you will. And they compensate each other. And I get something that is just uniformly 1 here and uniformly 0 here, if I add them up. Okay? But now if I want to simulate things, I'm a little bit of a precarious, in a little bit of a precarious situation, because I know the matrix element is actually not 0 outside this angular ordered region. There's just a positive and a negative part, okay? And a Monte Carlo with negative probabilities is also, it's not impossible, but it's a little bit harder to do, right? So do we have an alternative? And it turns out there's an alternative for simulating things. And both this picture and the alternative have their own quirks and advantages and disadvantages. Yes, go ahead. So W tilde is not measured directly, but the effect that you have radiation only inside this forward cone is measured. And the way you measure that is you, back in the 50s, by now you can, of course, measure it in a different way, but you take photographic film and you measure cosmic rays, essentially converting, or neutral particle essentially impinging on your film, converting into an E plus E minus pair. And then you see the blackening of the film developing gradually between the charges, which means that the additional radiation that you get off the E plus E minus pair will not develop right away, but only once the transfer separation gets large enough, something like this. So this is also described in the, I think in the Pythia manual and also in the book by Alice Sterling and Weber, for example.
You add those two terms together because the other term will have exactly the same thing on the other way, right? So you totally can't do the difference.
You mean here? Yeah, you can't measure those individually, obviously, because, not entirely obviously, but you can't measure those individually because, okay, they actually came from a function that was entirely positive, right? And that is our matrix element, that's physics. This thing is just how people like to simulate physics when they want to do angular ordering. So there's actually no negative probability. This is a consequence of how we did the matching in order to project it onto the collinear region. Does that make sense? Okay. So this is an artifact of thinking about radiation not being dipole radiation, but effectively monopole radiation, right? So we think about a parton zipping along, radiating something, and believe that we can simulate or calculate the entire radiation pattern just as a function of the momentum of that particle. And what this tells us is that we also need information about the charge partner of this particle, which was the other side of the emitting antenna, if you will, right? Because the charges never come isolation. Does that make sense? Okay. However, the interesting thing to keep in mind and to remember is that we only need information about the direction of the charge partner, right? Nothing else matters. According to this radiator function up there, we are sensitive to the energy of the field quantum, but we are not sensitive to the energy of the emitting particles. Okay. So now from here, we will try to approach realistic QCD. Slowly, by calculating the matrix element for 2 emissions. So for 2 emissions, in the region where we only consider either soft radiation, double soft radiation, or kind of the classical terms, semi-classical terms, we have a very limited set of Feynman diagrams that we need to calculate. And if so this is supposed to be the squared Feynman diagram. So this is like the for example, the construction of the state that Ian was already talking about, like the psi bar gamma psi or whatever you like, the creation of a charged pair, basically. You can have diagrams that look like this, and this is kind of the cut, right? Then you can have diagrams that look like this. You can have diagrams with a triple gauge coupling, where you cut through here, and you can have diagrams with a triple gauge coupling where both couple to the same. And then you have permutations of this, where the gluons or the attachment of the gluons to the individual Wilson lines is in different places. Okay. So the structure of this matrix element is very similar to the structure of this very simple QED type matrix element, because all we need to know is what are the charges that radiate. Okay, so let's first look at the color factors. And I encourage you to do them as an exercise. So if we think about the color factor of the crossed box, and let me assume that these two guys here were quarks, okay? So my initial color charges, and this is really just to make it more convenient, because if they were gluons, we wouldn't see any difference because everything comes with a CA. So I need something that has a different color charge to make this explicit what happens here, okay? So let's assume these two things are quarks here. So my matrix element here will be, or my squared diagram here will be proportional to CF times CA over 2 minus CF. And it does not matter for the color factor, and I encourage you to convince yourself of that, where you attach these gluons. So that squared diagram will have the same color factor as that squared diagram. Okay? So everything that is of this crossed box type will have this color factor. And the different color factor will be CF times CA over 2. And that's the one with the triple gauge coupling. Not surprising, because here I have a genuinely non-abelian structure, right? So it better be proportional to the Casimir operator of the gluon. And I encourage you to do that as an exercise. Okay, so these are the color factors, and then we do the kinematics. For diagrams of this type, or for squared diagrams of this type, we have, okay, so can anybody guess what the structure of this matrix element might look like? Thinking back to the discussion up there. What happens if I take this gluon out? So let's say this is a time-ordered process. I first emit one gluon, and then I emit another gluon. What would the matrix element look like? Okay, so the thing to realize here is that if you consider this as a time-ordered process, which, okay, you shouldn't really, because I'm calculating it in a different notation, but the physical interpretation still holds. This is nothing but the squared matrix element from over there, because I am emitting this gluon from the initial quarks, which are the initial color charges, and I'm just doing it twice, basically, okay? So this thing, if I slightly change my labeling, because it will be more convenient for our discussion here, so I'm doing quark with index 1, antiquark with index 2, and gluon, index I, index J. So I and J will be my hard Wilson lines. And then I have two gluons with labels 1 and 2. Then this will be a PI, PJ over pi p1, p1 pj, and then the same thing again, the pi pj over pi p2, p2 pj. So literally just the square, if you will, of that matrix element over there, right? So it's like, this is literally like QED basically, just the color factor is different. Okay. So now I'm calculating the non-trivial one, which looks like this, for example. And it depends on where exactly the gluon's attached, but I'm just giving one example here, and you can go through the others yourself. So here I can follow the same logic. I can say first I emit this gluon, okay, which gives me the matrix element that I know and love. And then I emit this one, but now it's not the original color charge that emits this. It's the new gluon, right? So it better be of the structure P1 Pi over P1 P2, P2 Pi. Because now the charge pair that emits is the pair 1i. Does that make sense? Okay. If there are questions, let me know. Okay. So from these 4 building blocks, I can now assemble the entire 2-loop soft matrix element, except for the virtual corrections, which I will gracefully gloss over here. You can find them in a paper that I have in the references. So the complete real emission matrix element squared is then given by the original charge factor. And okay, for convenience, I will write Sij here as 2pi pj. Oh, the light's not on, right? Yeah, okay, thanks. Okay, so just to abbreviate this a little bit, this will be Sij over Si1 S1j, and then Ca over 2 with the genuinely non-abelian structures Si1 over Si2 S12 plus Sj1 over Sj2 S12 plus Cf minus Ca over 2 Sij over Si2 Sj2. Okay. So these 2 terms essentially come from the fact that this gluon here can be emitted either between those 2 charges or between those 2 charges, basically. And okay, this is arbitrarily normalized, so don't take it too serious. I should put a proportional here, okay? Obviously, there has to be a strong coupling as well, and which I also ignored. But the important thing to notice here is the structure in terms of color charges and kinematical factors. Okay, go ahead.
Is there some meaning to when you are and are not drawing the cut?
Right. So for the kinematics, it does matter how I do this. For the color, it doesn't. And you can convince yourself that when you add up everything correctly, you get this. So to understand the structure, understanding those is enough. And you have to go over all permutations and get the factors right, and you will arrive at this, this equation here. I should say that this is in the strongly ordered limit. So what I'm assuming here is that the energy of E1 is larger than the energy of E2. But the structure doesn't change very much when you go away from that limit. You go to double soft limit also.
But I suppose they all have the cuts, even the ones you drew at the bottom right?
Yes.
Like otherwise it's a...
Yeah. Sorry. Oh, sorry. Yes, of course. Yeah. So that's supposed to have a cut. Yes. Sorry about that. Okay. Good. Good. So there are non-abelian and abelian type color factors here. So what is interesting to note is that this factorizes into a first emission and into a second emission type term, where you can kind of read off between which charges the second emission has happened. And also interesting is that this similarly abelian-looking kinematical factor here mixes with the non-abelian charges, right? And that's because of this diagram here, the squared diagram there, basically, right? And then this color factor. Okay, so we can take two limits on this. We can take NC to infinity, large NC limit, in which case this thing will go to, okay, so I take NC to infinity, but I hold CA fixed, okay, so it will be CA squared over 2 times Sij over Si1 S1 to S2j plus Sij over Sj1 S1 to S2i. And I don't know in how much detail the Park-Taylor formula was maybe discussed in the Amplitudes lecture. Was it mentioned? No? Okay. So this is literally just the square of a maximally helicity violating scattering amplitude. And we can discuss in the tutorial how this emerges. Okay, and then we can also take the abelian limit, if you will, the NC to 0 while holding CF fixed, which will be CF squared Sij over Si1 S1j Sij over Si2 S2j. Again, as I said earlier, literally just the square of what we have up there, because the theory in that case behaves like QED, because I take NC to 0, basically. So the physical limits make sense. Okay, in order to see that this physical limit makes sense, you can write this in this form and basically realize that as soon as a new gluon has been emitted, say I go from here, sorry, I have an initial pair of color charges. Let's say I do this with color. So they are color connected. And in the large NC limit, I can literally think of every gluon creating a new color charge, which has a different color, quote unquote. So after my first emission, there's still the original color charge, but that is now between the initial gluon and, between one of the initial quarks and the gluon, and there's a new color, okay? So it breaks into two, kind of, the way people like to talk about it is we break the initial dipole into two dipoles, and each of those radiates individually, and we have to take the product of the two radiators, and that's precisely what happens here. Does that make sense, this picture? Okay, great. Questions? Good. Yes?
When people go beyond leading color, are they just including more interference effects between different branches of the shower?
Very good. So the question is, when we go beyond leading color, do we include more interference effects? And the answer is yes. And there are different types of those. And we can discuss in more detail during the tutorial. These types are typically very easy to take care of. Because if you think of what CF minus CA over 2 is, that's 1 over 2 NC. So compared to the leading color, which is NC over 2, this is 1 over NC squared suppressed. So this is very, very nice. However, that has to do with the fact that we have a trivial structure at the leading order, which is really only one pair of connected color charges. As soon as you have more structure in the matrix element, in particular, as soon as the kinematics at the Born level starts to mix with the color, let's say you have a dijet process that was produced at a hadron collider, it gets more complicated because different partial amplitudes in the language of the tutorial from 2 days ago start to mix with different structures. And then I cannot simply do the color trace here to find these factors, but I really have to do a matrix multiplication. Sorry. I have to do insertions of the soft operator over there, including 2 color operators into the hard matrix element and exponentiate this in the Parton-Shao. And that becomes very complicated, right? So the evolution really turns into a matrix evolution. And we can discuss the details maybe later in the break or during the tutorial. So that is the challenge now. So the subleading NC effects, which are effects like this one, they are fairly easy to include. And it becomes progressively more complicated. And in particular, a full color evolution involves a full matrix evolution of the soft operator, and that is really challenging. Because you also, the problem is you get a lot of negative weights. So the matrix element, so the matrix evolution by itself is not the problem. The problem is the negative weights. Okay, good. So next thing we would like to do is to visualize this, because even though we have a kind of a more or less intuitive interpretation of what happens here, we really don't have a good grasp of what it means in terms of these Dalitz plots that I put on the other board. And that will take us to the Lund plane. So the Lund plane, Lund is a city in southern Sweden, was invented in Lund in the late 1980s. And it was the basis for the construction of a lot of terrific Monte Carlo programs, which were used in the Petra, Leb, and Hera days and are still in use at the LHC today, going by the names of Pythia and the like. Okay, so in order to introduce the Lund plane, let me go back to the picture of yesterday, where I said I choose a coordinate frame where my initial charges, and now I'm using the language from here, so I call this Pi. Sorry for the change in notation. And I call this P1 again. It will just help me because I will need 2 emissions later on again. So these 2 momenta don't have a transverse component. This here is purely plus. It only goes in the forward, so it goes in the forward direction. This here is purely minus in the notation of P plus minus being E plus or minus PZ. And then the emission has a transverse momentum, so P1 perp, and a rapidity, which because everything is massless here, I call pseudo rapidity eta C. Sorry, eta 1. There it is already. Bless you. Okay, so I can write my momentum P1 as a plus component, plus a minus component, plus a perp component. So these are supposed to be Lorentz indices, okay? And I can project out the individual components by saying, okay, P1 plus, for example, is the dot product of 2pi dot P1 over square root of 2pi Pj. If I normalize it appropriately, okay, I have to normalize Pi and Pj appropriately, but let me assume they are normalized, and I can do the same thing for the minus component, Pj P1 over root 2 Pi Pj. Okay, so there's still some normalization issue here, but it will drop out in the end for what I need. Also, I know the on-shell condition for P1, which is P1 plus, P1 minus, minus P perp squared. Okay, so here P perp is a 4 momentum. Here P perp is a 3 momentum, but I will skip the vector notation, okay? Right. So we already said that the matrix element on the far left of those blackboards can be written as the transverse momentum squared of 1. So this is the inverse of my of my soft matrix element or semi-classical matrix element, which is very convenient because I know that the matrix element is 1 over pt squared in this notation. And I can also calculate the rapidity using these formula here. And this is where the normalization drops out, and this is why I didn't care how I normalize it. This is just the logarithm of pi p1 over pj p1. Okay. Okay, let me try to simplify or to rewrite this. So let me rewrite this rapidity. I can say, again, using these relations here, this is either 1/2 times the logarithm of 2pi p1 squared over p perp 1 squared pj p1. Sorry, pi pj. Sorry, pj, making a mess here. Or I can say this is 1/2 log of p perp 1 squared times pi pj over 2 p j p1 squared. Essentially different ways of writing the plus component over the minus component with the help of this relation up here, because I have the on-shell condition and this has to be 0. Okay? Now let's think about what happens when our emitted particle, which goes by the index of 1, is in the collinear region. Collinear to, let's say, pj, so kind of anticollinear to pi. Then this thing will turn into pj times some factor. And if the energy that the emission carries is very large, this will turn into the total center of mass energy of the system. Okay? And the square will cancel against this factor down here, and the same will happen here. So from this, I can infer the phase-space boundaries in this notation, in this particular frame, which are 1/2 times log of, let me say that I have S equals pi plus pj plus p1 squared. So this is the total center of mass energy, okay? So this will be minus 1/2 log S over p perp 1 squared. Has to be less than the rapidity of 1, less than plus 1/2 log S over pt1 squared. That's a very simple formula, okay? And it is super convenient because now I can start drawing. And I put various pieces together. I know that my matrix element, the matrix element on the far left is just the inverse of this, right? A differential matrix element.
I have a question.
Yes, go ahead.
Oh, never mind. That's the total momentum.
Yes.
Mass. Okay.
Yeah. It's the invariant mass squared of the entire system, basically. The dipole invariant mass. Other questions? Okay. So the matrix element is just 1 over p perp squared, right? So let me put this here. Okay. Yesterday we derived that the phase space for the emission of that additional particle, which I call +1 because we make one more particle, is dp perp squared d eta, which essentially came from the fact that it's proportional to dp1 plus dp1 minus, okay? So by means of the definition of the rapidity, I can calculate that this is the same up to a factor 1/2. So there's no Jacobian there. Okay, now this is very convenient because as I put the phase space together with the matrix element, I get the total radiation probability. And the radiation probability apparently is d phi plus 1 times matrix element squared. And I'm skipping the constants here, which is a dp perp squared over p perp squared d eta. Okay, so it's a d log pt squared d eta. So is that okay? Okay. I also know these phase-space boundaries on the rapidity. So let me start drawing. I draw a plane where I put rapidity of 1 here on the abscissor, and I put the logarithm of pt squared over s on the ordinate. So my allowed phase space has to have pt squared smaller than s, right? So it's all in the third and fourth quadrant of this plane. And I know that this is essentially the diagonal in the third and the fourth quadrant, which limits the phase space for the additional radiation. And I know eta has to be in between. So the allowed phase space is here. And depending on how low I want to go in my transverse momentum for the emission, I know at some point it has to cease because QCD will turn non-perturbative, and I cannot keep calculating things with perturbation theory. So pt squared better has to be larger than something of order lambda QCD, right? That will kind of define the absolute minimum here in this plane down to which I can calculate my matrix element, okay? So now I'm in the situation that I explained in the very beginning of the lecture, where I have a plane into which I'm throwing darts. And I can Monte Carlo this. I have a uniform probability for QCD radiation in this plane. So if I can throw darts uniformly into this plane, I will faithfully simulate QCD, in this approximation at least. Does that make sense? It's a very simple, purely geometrical picture derived from the semi-classical approximation. And this is why it's so famous and yeah, nowadays even used in experimental measurements. So it's measured in this way at the LHC nowadays. Okay, so let's say I throw a dart into this plane. That's now a gluon that I generated. Okay, what happens when I throw a dart in this plane when we think about this matrix element here? So that was my first emission, basically. What happens now? Thinking about this structure here. Okay, you generate a new color charge. And when you generate a new color charge, you open a new phase space for more radiation. Okay? That means at the very moment I generate this gluon, I generate a new Lund plane, which I can visualize by saying, okay, I take, let's say, so this is my Lund plane that I generate. Let's assume that this was a triangle, okay? I take this triangle, I fold it, and I stick it on the original Lund plane, okay? So I still have the same area because area is probability. I should not change the area. But now it kind of sticks out as a separate plane from this original Lund plane, and it has a front and a back side, and both are responsible for additional gluon radiation. Okay? I can iterate this. I can throw another dart in here, generates yet another Lund plane. I can throw a dart here, generates yet another Lund plane. I can throw a dart here, and so on and so forth. And I can keep going. And what will develop here is known as the Koch snowflake. It's a fractal. And you can calculate the scaling dimension of this fractal, and it's connected to certain properties of QCD. Okay? So the scaling dimension of this, if the strong coupling is not running, is NC times alpha S over 2 pi. The square root of that and a 1 plus. Okay, so that's your anomalous dimension for this fractal. And what it means is like, okay, in order to say I have an anomalous dimension, I have a fractal, I have to do something to this. So I basically cut it at some value of transverse momentum, at which point it turns into just baseline of this fractal, which will look like this. So this fold that I generated in this from the original Lund plane, which is also called a secondary Lund plane, will then stick out here as a baseline. This new gluon will stick out here, this will stick out here, and this will stick out here, okay? So this thing is also known as the origami diagram, because it's a bit like, as you could see, me folding this thing here is a bit like doing origami. Okay, questions on this? Okay, then let's keep going. No, it's just to visualize it, yeah. Actually, maybe I want to keep this and I stick to this. Okay. So now we look at our approximations here at the large NC limit and at the NC to 0 limit in this picture. Okay. So in the large NC limit, we have a Lund plane, and the probability for emitting the second gluon, for which I need to have emitted a first gluon, which means I already have this fold, is proportional to Ca over 2 squared. So all the Lund plane is kind of colored with the same color charge, which is Ca over 2. Okay. In the NC to 0 limit, in the abelian limit, I have a Lund plane, another gluon is sticking out, and the entire Lund plane is colored with the color charge of the original charges, which is CF, basically. Well, strictly speaking, I had the Ca squared here for the total thing, but you know what I mean? Okay, clearly QCD has to be somewhere in between. What does it look like? That's what we're trying to find out. In order to find that out, we can take this matrix element here, the full thing, and we write it in terms of these radiator functions, which are projected onto collinear regions. And when we do so, we find that this is Cf over P1 perp squared, 1 over E2 squared, Ca over 2, Wi12, you don't need to write this down because it's all in the lecture notes, which are already online. I just want to explain how it's done. Plus Wi121 plus Cf Wij2I plus the flip notation, the flip thing. Okay, so the reason why we have done this is because we want to somehow get rid of minus signs. And the most convenient way to get rid of minus signs is to combine these two functions into one, which we can call W bar. And it turns out that this function is suppressed in the collinear limit. This is single soft. That means it contributes only in the wide angle soft region. Okay? Now, once I know that when I smoothly integrate this function, it must vanish when the angle between the first and the second gluon, let me write this down, is less than the minimum of the angle between the original Wilson line and the first gluon, or the angle between the original two Wilson lines. Okay. We also know that azimuthally integrated, these W tildes, that's what we proved up here, vanish if the opening angle between the emitter and the charge is larger than the angle between the original charges. Okay? So from this, we can piece together everything. We can draw a Lund plane with two emissions. Or let's say the Lund plane which generates the second emission. So the first one's already there, okay? And we put the first emission slightly to the left of the middle, which helps us understand what's happening here. So this is eta equals 0. This is some kT for the first emission. The second emission happens at smaller kT. And if, according to this, the angle between the two emissions is less than the opening angle between the original charges and the emission, this stuff here vanishes, and I will radiate with a color factor of CF, which means that, translated to the Lund plane, in the back plane of the Lund diagram, you have a color charge CF. And only on this fold, where the new gluon sticks out, you actually have a color charge of Ca over 2. So that is the correct radiation pattern for two emissions. And you can derive it from this structure here, which is complicated but not too complicated, by splitting it into collinear radiators like so, and partial fraction soft radiators in the angular ordering language. So whenever you see discussions about the logarithmic structure of parton showers and whether it faithfully reproduces the subleading color factors, have this picture in mind, okay? Questions? Yes, go ahead. I have to think about this. Let me get back to this question in the break. Okay, so now we want to build a parton shower. And I think I have just enough time to build the two most favored approaches of parton showers based on the knowledge about QCD radiation pattern that we now have. So we discussed the factorization formula for phase space. We know that I can factorize an n+1 parton phase space into an n parton phase space, an integral over some assumed propagator and a two-particle decay. And I know that this d phi 2 here contains a loop factor and a polar angle integral and an azimuthal integral. And I use the same mapping as what Ian used this morning to rewrite my cos theta integral into a z integral. Okay? So that this combination here will turn into a dp squared. Sorry, there's no 2 pi here. Whatever, let me ignore factors of 2 pi. We can always find them later. So there's a 1 over 16 pi squared here. There is a dz here. And there is a d phi over 2 pi here. Okay, so this is the phase space. It's exactly the same as this phase space, which I did in a somewhat sketchy way. Just in different variables, okay? So kind of going back from the dipole type radiation picture to the monopole type radiation picture or collinear evolution picture. I know that my single emission matrix element that is up there has this form of an Eikenau. And I can define a splitting function for flavor, for non-flavor changing splittings, basically as the product of PA, PC, or in the notation of up there, sorry about that, times the full matrix element squared, which means I take the propagator factor here out, okay? Because I want to combine it with this one. Okay, so then my total radiation probability, which is the phase space times matrix element squared, just like down there, but in a different language, will be a D, and let me again do it a little bit sketchy. Actually, no, let me do it exactly. PAPC over PAPC. dz alpha s over 2 pi times PAA of z. Okay. Okay. So this is the same probability density that I wrote there, but I wrote it in a slightly different form. And what I would like to do now is I would like to say, oh, again, this is obviously a logarithmic integral here. And it's of type dt over t, where t is pa.pc. Okay? I can rewrite this as a dt over z times 1 minus z by t over z times 1 minus z. So I just do a little variable transformation without a Jacobian because I'm only dividing by something that depends on the second integration variable. And now I call this thing q tilde squared. It still has dimension GeV squared. But it actually behaves like an angle, okay? So assuming that the energy of the emitted gluon is small compared to the radiating particle, I will have essentially an angular evolution here. And since I know that eta is log cotangent theta over 2, I can relate these two, and this is essentially, if I draw this in the Lund plane, an evolution in rapidity, although not quite, because this relation here only works approximately, okay? So what happens with an angular ordered parton shower, which is what this is, think, when you see this, think Herwig. You have the Lund plane, and Herwig will fill the Lund plane from the center to the edges with like artifacts that are due to the fact that this is not exactly an angle, okay? So the evolution in Herwig will go from the center of the Lund plane towards the edges, okay? Now this is connected to the fact that Herwig is next to leading log correct for global observables. Why is that the case? We said here that the back plane of the Lund diagram should produce radiation with color charge CF. And then only the fold of the gluon should produce radiation with color charge Ca over 2, okay? Let's assume that we are evolving in the forward direction, right? So these are contour lines of equal evolution variable, these things that I was drawing here, okay? So along these lines, q tilde squared has the same value, okay? And so we're going from large q tilde towards smaller q tilde as we follow the gradient of these contour lines, okay? So since we evolve from the center to the edges, okay, does somebody know what that means for transverse momentum? Because transverse momentum is on the ordinate axis of this, right? We evolve along the abscissa. What does it mean for the ordinate? Okay, so this is my ordering variable. A parton shower can only have one ordering variable. The other one is the splitting variable. The ordering variable, as the name says, it's ordered. The splitting variable is not, which means that when Herwig does the evolution, it's an evolution in rapidity in the Lund plane and a random walk in transverse momenta. That means in Herwig, I can generate an emission at very small transverse momenta first, and then at a later stage, at larger rapidity, generate a transverse momentum that is much larger. And this is kind of counterintuitive because we think about QCD in a way that the first emissions should always be the hardest, right? But it's not actually necessary because I said I can throw darts in this plane it has uniform, if I have uniform probability of throwing darts, I will faithfully represent the QCD radiation pattern, right? So this is how Herbig does it. Let's say we generated this gluon here. Now, because Herbig evolves as a parton shower with the color charge of the radiator in a parton language, everything that will be generated in this primary Lund plane will have been generated with the color charge of the initial quark. So this gluon will have been generated with CF. Any other gluon will have been generated with CF. So that means everything that comes off the backplane in the Lund diagram will have color charge CF. And only the stuff that is generated from those folds, once they have developed, will actually have color charge CA. And that is precisely the picture that we were developing here, and this is why Herbig is correct at next to leading log. Okay, does that make sense? It is a feature of the angular ordered evolution. Okay, and you can go to the old papers by Brian Weber and Giuseppe Marchesini from the 80s who proved this in a very nice way. Okay. So this is angular ordered parton showers. Now we go to transverse momentum ordered parton showers or dipole showers. In fact, I almost don't need to do this anymore because we did it here. In a dipole shower, you do the opposite. You say exactly what I said before. After factorizing the phase space, I say that my light cone momentum fraction actually gets mapped to 1 minus PA/PC over PA tilde PB tilde, which is or let's call it S before I called it S, minus PA/PC times e to the minus 2 eta c. So that's a mapping between Z and the rapidity. That's the exact mapping. The one over there is approximate. That gives me the differential radiation probability in a different language. So dp becomes d phi plus 1 times matrix element squared. And my splitting function is now defined, my flavor non-changing splitting function is now defined as p perp squared times matrix element squared, which gives me a dp perp squared over p perp squared d eta times alpha s over 2 pi PAA of z. With this definition of the splitting function, so let me call it p tilde. So now, okay, one thing that I didn't actually say here is that the first integration variable here, I consider my ordering variable, okay? So I produce an ordered sequence of emissions ordered with respect to what I have here, okay? Because I don't like virtuality, I use this q tilde, ordering therefore in rapidity. Now my first integration variable is different, it's the transverse momentum. So ordering therefore in transverse momentum in the Lund plane, this means that I evolve from the top down because I order in transverse momentum, and this was log pt squared over s, and this was rapidity. So my contour lines now look like this. This is a little bit of a problem because when I produce gluons, let's say I produce a gluon here, it's ordered in PT and a random walk in rapidity. And at the very moment I produce a gluon, I open up a new dipole. And I said earlier, okay, in principle, I take the phase space of that dipole, I fold it, and I stick it on, but that's not actually how the showers work, how the dipole showers work. The way they work is more like what we had on the other blackboard before, that you have the color string breaking into two lines. Now these two dipoles evolve independently. In the Lund plane language, this means that this fold evolves together with this half plane further towards smaller pt, and the other fold, the other side of the fold evolves together with this half plane. And because they are considered as a new primary Lund plane, where the forward direction radiates with a color charge of CF, and the backward direction radiates with a color charge of Ca over 2, because this is a gluon, you now only have half of the backplane with a color charge CF, radiating with a color charge CF, and part of the backplane radiating with a color charge Ca over 2. So therefore, this is not a faithful representation of the matrix element at subleading color, at the first subleading color term, because you color half of this backplane with a wrong charge. And this is the reason why the original formulation of the dipole showers from the Lund era is not next to leading log correct. However, once you know this, you can easily correct for it because you just analyze where your emission is in terms of rapidity in the primary Lund plane, and you can reweight your parton shower with the correct color factor. Okay? But you have to do it. And this picture becomes progressively more complicated as you have additional emissions, because you can have a situation where those two gluons here, for example, are color connected, which means that the entire backplane in between would be quote unquote colored with charge Ca over 2, and therefore radiate with too high probability. Okay? So much of the discussion about the logarithmic accuracy of parton showers is tied to this. There are solutions that were already proposed in the late 90s how to fix this, essentially by analyzing the rapidity segments in the Lund plane and then just correcting with the right color matrix, with the right higher order matrix element. And it turns out that you can actually, because this is an ordered sequence of emissions, you can actually iterate this procedure, and it works at any orders, at any order, as long as you're not thinking about higher logarithms than next to leading log. Okay, so in my last 5 minutes, I would like to flash a couple of slides that will give you a flavor of what I have to do here. Okay, this thing went to sleep. Of the additional higher order corrections that we would like to include. Oh, it says battery is low. Do we have a? Oh yeah. Okay. I think it is connected. Okay. Shouldn't be a problem. Okay. Continue. No. Okay. You better do it. Yeah, I'll do that. Sorry about that. In the meantime, are there questions on this? Go ahead.
So I know that when Pythio organizes the shower, it will steal some momentum from elsewhere in the shower before each splitting.
Yes.
So will Herwig do this as well?
Yes. Okay. And no. Depends on which version of Herwig you're talking about and which shower you're talking about. So the original formulation of Herwig, and this is connected to a topic that I don't have time to discuss today. This is another part of the next to leading log accuracy discussion. The original version of Herwig was constructed such that the momentum shuffling would only happen at the very end of the shower. That was Herwig, everything up to Herwig 6, basically. Since Herwig++, the momentum conservation is implemented locally in the way that I explained in the first lecture, where I was drawing this picture where you have 2 incoming partons and then you reshuffle something in order to put the third one there and have finite transverse momentum. It turns out that if you do this in this picture, you violate the next to leading log accuracy, not only because you have the wrong color charges, but also because when you have a second emission here, that steals a bit of momentum from this one, you can drastically change the matrix element that should have been implemented here. In other words, you reconfigure your configurations, you reconfigure your Lund plane so much that the original matrix element with which you calculated the first emission is not valid anymore. And this is a logarithmically enhanced effect, which is why it's problematic. So you cannot say it doesn't matter. So the original version of Hoeche, which is the funny thing, already had this correct. It was only with the move to the dipole showers in the LHC era, where we were all fond of local form momentum conservation because the matching to higher order corrections is much easier in this way, that this was changed kind of, and at the same time in all showers, basically. What's also interesting is that the original version of Pythia also is more next to leading log correct in this respect than the current version. And this has, again, to do with the fact that the problem occurs predominantly in the dipole picture. And everybody moved to dipole showers, basically, in the LHC era. So now we have ways that we can combine the niceties of the dipole shower in the sense that we just evolved down in the Lund plane, and therefore we have an easy matching to the higher order corrections with the next to leading log accuracy. And the gist of it is that whenever you generate a second emission that would put significant recoil somewhere, you better don't put it on another soft emission. You put it on something hard, your original Wilson lines, essentially. That's kind of the gist of what everybody is doing these days. So if you read a paper from Panskills or a newer paper from Sherpa on this topic, it's all about how can I redistribute the momentum such that when KT becomes small, it is a parametrically small effect because it is suppressed by the high scale of the energy of the original Wilson lines, basically. Does that make sense? Okay. So it's actually, in retrospect, it's very simple to understand. But one has to fix it because it generates real trouble if you don't. Okay, so you find everything that I discussed also in the slides, and I only have 1 minute left, unfortunately. But one thing that I would like to encourage you to do, because this is the other thing that always comes up in discussions about the parton shower, is that there is a set of universal higher order corrections that are implemented in every parton shower. And this goes by the name of the CMW scheme. And this is, again, an abbreviation with names of people. This is Catani, Marchesini, Weber. The original paper was written in 1990. And the idea is as follows. You have universal higher order terms that are not the ones that I was drawing, which were the soft terms, but these are soft collinear. So you emit a gluon from your Wilson line, and you split your gluon using a collinear spin-dependent splitting function into two, either gluons or quarks. And you do the honest higher order calculation in d dimensions, including the virtual corrections, and expand your result in terms of a Laurent series. I don't have time to go through this, but the result is very interesting because what you get is this structure up there for the order epsilon terms from the expansion of the phase space. So the logarithms that you see that you will see on the next slide essentially come from the fact that there's an epsilon power here, which comes from the dimensional regularization. I can expand this in powers of epsilon, then I will get log z1 minus z type terms here, right? They can hit a pole from the collinear limit and will give a finite contribution and become of this type. There are also genuine 1 over epsilon terms, which are the first terms.